Next, we're going to look at the factor theorem and example 13.9 to help us see how the factor theorem works in practice. I'd like to start with example 13.9 because there's some things about it that we already know how to do. And then when it comes time to actually using the factor theorem, then we'll go back and we'll address what the factor theorem says. Example 13.9 starts with saying divide, and it says f of x by x plus 1. So we're going to be taking the f of x and we're going to be dividing it by x plus 1. So in other words, we're going to take x cubed minus 4x squared plus x plus 6, and we're going to divide it by x plus 1. So that is perfectly in position for us to use synthetic division to complete that division process. So we're going to go through and set up with 1, -4, 1, and 6 to represent the dividend. And then we're going to use -1 to represent our divisor. And we will bring down the 1 and begin the process. So -1 times 1 gives us -1. -4 plus -1 will be -5. -1 times -5 will be +5. 1 plus 5 will be 6. And then -1 times 6 will be -6. Then I add that last bit together and I end up with 0. So we know that the synthetic division gives us both the quotient and the remainder here on that bottom line. Here's our remainder, here's the constant, that's the x coefficient, this is the x squared coefficient, and then those last three values all together are going to help us to create the quotient for this division. Now, we've done the division, but then it says, then use the remainder and factor theorems to completely factor f of x. The remainder theorem doesn't say anything about factoring. The remainder theorem says that if we have a division problem of the form f of x divided by x minus c, then we are permitted to use the remainder from that division process to represent a function value. So that's exactly what's going on here. It told us to perform a division with f of x divided by x plus 1. So the value that we have here is -1, and the function value for -1 is the remainder that we just came up with, which is going to end up being just 0. So we get that conclusion by the remainder theorem. So that's the first part. Now it says that we're also supposed to be using the factor theorem. So let's see what the factor theorem says. It says let f be a polynomial. We have that. Let c represent a real number. We already have that. And number 1, if f of c is equal to 0. Okay, so for our purposes right now we have -1 is c, which means f of -1 would have to be equal to 0. Well, would you look at there? We already concluded that f of -1 is going to have to be 0, and the remainder theorem told us that. So the remainder theorem ends up being a gateway for us to be able to get into the factor theorem, because that's what's able to get us into the f of c equals 0. So if we have f of c equal to 0, then what can we conclude? We can then conclude that x minus c is a factor of our function f of x. So x minus c is the x plus 1 that we were using in the division. So now I can make another statement that says x plus 1 is a factor of f. Or really, it's a factor of f of x. Now that's really fascinating. So synthetic division, if the remainder is 0, will actually simulate a factoring for us. And it's even bigger than that. So take a look. If I perform the division, which we've already done, and I write out the answer to the division problem is going to end up being x squared minus 5x plus 6. And I don't have to include anything else because the remainder is 0. So look at this statement right here. We have this interesting statement. And then if I was to multiply both sides of that statement by x plus 1, then I would end up with the following statement. I would end up with x cubed minus 4x squared plus x plus 6 is equal to x squared minus 5x plus 6 times x plus 1. So not only is x plus 1 a factor, but x squared minus 5x plus 6 is also going to be a factor. So there's more to this factor theorem than meets the eye. It says that we're supposed to use it to help completely factor, not just find one factor, but get all of the factors. So what this is saying is that f of x, which is x cubed minus 4x squared plus x plus 6, is now equivalent to x plus 1 times x squared minus 5x plus 6. That is the divisor, and that's the quotient. So anytime you get a remainder of 0 from your division problem, then you can always take the divisor and the quotient from that division process, and you can put them together as the factors for the original function, which is your dividend. Hugely important theorem here, and we will be using this quite often throughout the rest of the semester, especially here in this polynomials set of sections. So the factoring has been started, and we can even take it a step further. We can say the x squared minus 5x plus 6, that will factor into x minus 3 times x minus 2. So not only does the synthetic division perform factoring for us, it allows us to then get a linear factorization for our function all at the end. So we end up with 1, 2, 3 factors, all are degree 1. Add that up, you get degree 3, and your original polynomial was degree 3.